A very warm welcome to everyone joining us today on Ekahau's webinar, and we are continuing our Demystifying Wi-Fi series. And in today's show, we're going to be covering channel planning. It's such a vast topic to get your head around and understand, so we're going to do our best to cover as much as possible about channel planning during today's webinar. We're really excited to talk about channel planning because we think it's one of the most critical things that we need to know and understand to be able to design a high-performing wireless network. So who are we today on the show? Well, you've got myself and Mac, the directors of product marketing and ECSE here at Ekahau, but we also have our first time guest helping us with the Q&A, and it's Mr. Dale Tyler. So Dale, how are you, my friend?
Doing good. Glad to be here with you all. Thanks for having me today.
It's a pleasure, man. And actually, it's not the first time. I think both me and Dale, we were guests on one of Ekahau webinars before we were at Ekahau. So that's funny that we are here again together.
Yep, it's my first time on the Ekahau side, but previously I was on as a guest when before I joined in Ekahau.
Nice to have you here, man.
Thank you.
All right. So what we'll be covering in today's webinar, well, we're going to be talking about Wi-Fi channels and how should you plan for them for your Wi-Fi networks. And we're going to be looking at the differences between the Wi-Fi channels in the different frequency bands.
Easy peasy, lemon squeezy. This is such a vast topic. We will try to keep it a little bit on a higher level side, because we can very easily go into a rabbit hole where we will feel the urge to talk about more technical concepts. We'll try not to do that. So we will talk about channel planning. As Matt said, we'll focus today on 2.4 and 5 gigs, especially for 6 gigs. We'll have entire different series. So keep your eyes peeled for that before you ask. And then at the end of the webinar, we have a very special announcement about the update to one of our products with updated Ekahau Insights with extremely cool functionality. I hope that you will have your brains smashed as much as I have mine.
Yep, and we're going to have some live demos for you as well and show you how you can do channel planning inside of our awesome tool Ekahau Pro. So first of all, let's get started and let's talk about the 2.4 gigahertz channels. And before we start talking about the 2.4 gigahertz channels, we really just want to say, depending on where you are in the world, you're going to have different access to different channels, different rules, different regulations, different transmitting power levels you can use, different rules for indoors, for outdoors. So please always make sure you check with your local regulatory domain around the Wi-Fi channels that you can use in your region. But first of all, let's take a look at the 2.4 gigahertz spectrum. And if we take a look at what we can see here, it looks like we can use something called channel 1 through to channel 14. That's not really the case. Only channel 14 can be used if you're inside of Japan. Whereas the rest of us in Europe, we can use channels 1 through to channel 13. But some people that are joining us from the US, you might be thinking, hey, when I do a design inside of Ekahau, I don't even get to use channel 13 because inside of the US, you can only use channels 1 through to 11. Well, what are Wi-Fi channels? And we were discussing quite recently about kind of like a nice analogy of what Wi-Fi channels are and how they sit inside of the frequency spectrum. So if we think about like the 2.4 gigahertz frequency spectrum and then the channels inside of it, and we want to try and compare that to an analogy, if you imagine that when you've got a radio and you're trying to listen to a station, let's pretend that you're on like the AM side of the radio and you're trying to tune in to listen to a radio station on a particular channel, and you're moving through that channel, and then you can, pick a frequency, a channel that you want to be on inside of that station so you can now listen to it. Well, that's kind of how Wi-Fi works, and the channels inside of the frequencies that we want to tune into a channel inside of the frequency spectrum that we're using to be able to communicate over the air using Wi-Fi. So when we're doing a Wi-Fi design on 2.4 gigahertz, if we've say got 4 access points, do we put our first access point AP1 on channel 1, and then we put our next access point AP2 on channel 2, then our next access point AP3 on channel 3, then another access point AP4 on channel 4? And well, we probably don't want to do that. And why don't we want to do that? That's because we have something in Wi-Fi in the 2.4 gigahertz spectrum called channel overlap. So if we take a look at this image that we can see here, if we look at the 2.4 spectrum in this picture here, and we're looking at the 22 or 20 megahertz wide channels, depending on what standard of Wi-Fi we're using here, we can see that channel 1 that's highlighted in green, and then channels 2, 3, and 4, you can see that they overlap with each other. Whereas if you look at, say, channel 6, which is highlighted in yellow, and then channel 11 that's highlighted in orange, they do not overlap with each other. And Mac, I'll let you talk a little bit more about channel overlap in 2.4 and the size of the channels.
Of course. Thank you very much, Matt. So in 2.4 gigahertz spectrum band, our channels are either 20 or 22 megahertz wide. Historically, we had 22 megahertz wide channels with old legacy generations of Wi-Fi. Today, with OFDM modulation, we have 20 megahertz wide channels. And 2.4 gigahertz spectrum band was introduced before Wi-Fi was a thing, where we didn't know how wide the Wi-Fi channels are going to be. So channels 1, 2, 3, 4, all the channels in 2.4, they are 5 megahertz wide. So from Wi-Fi perspective, 20 megahertz wide channels perspective, channel 1 overlaps with channel 2, 3, and 4. And the first channel that it doesn't overlap with on 20 megahertz channel width is channel 5. But because of what Matt has mentioned, differences in regulatory domains and differences in channels available in different countries, it is the best practice to stick to channels 1, 6, and 11, 3 non-overlapping channels, because even if you have 4 or 5 channels available if you're in Japan, most of the vendors out of the box, they will have channels 1, 6, and 11 enabled by default. And we will talk you through why and how it matters, what happens when you have overlapping channels, like overlapping on the same channel and overlapping on adjacent channel. So Matt, yeah, could you?
Sure.
Yeah, cool.
Sorry. So yeah, so when we look at the 2.4 gigahertz spectrum here, it seems that, if you're inside the US, you can do like a 3-channel plan, 1, 6, and 11. But if you're inside of Europe, for example, you can do a 4-channel plan where the channels do not overlap, channels 1, 5, 9, and 13. And why is it that we don't recommend that? And we are saying stick to just channels 1, 6, and 11. That's because in our experience, we have never gone to an environment where there has never been any other 2.4 gigahertz wireless networks around you by your neighbors or surrounding buildings. They've got their own wireless networks, and they're going to be using channels 1, 6, and 11 typically as well. So if they're using channels 1, 6, and 11, and you're using a 4-channel plan of 1, 5, 9, and 13, why is that bad? And that's because that causes something that's called adjacent channel interference. So when we look at this graphic here, we can see that now, let's say in this example, they've picked to use channel 3 and channel 9. You can see how much that overlaps with channel 6. So why is that a problem? And to just kind of keep it as simple as possible, when you have adjacent channel interference, this is like Mac trying to talk to me in Polish. I've got no idea what he's saying. I don't speak Polish. I don't understand Polish. I have no idea when he's going to stop talking. So then I can have my turn to start trying to talk. So the reason why we say stick to 1, 6, 11, because if you are going to have other access points and their radios on the same channel as you, it's much better to have what's called co-channel interference or co-channel contention, where you've got other radios on the same channel, because this now means that when Mac is talking to me in English, I can understand what Mac is saying. I speak English. I can understand when Mac's talking English, some of the times anyway. But I know when he's going to be finished talking, so then I can understand when it's my turn to be able to talk, because Wi-Fi is a listen before you talk protocol. So if it detects that anyone else is trying to transmit or talk when over on the air when you want to be, it will back off, let them finish talking before they will try and talk. Typically, anyway.
Typically, yes. So in Wi-Fi, channel planning is quite difficult because we have different bands, we have tons of different channels. So if you could switch to the next slide, Matt. This is just like a high-level example of how do you plan your channel plan. So theoretically, what you would like to have is you would like to have a frequency reuse. So when you move throughout a different part of the building, you would like to be in range of different APs, different radios, broadcasting using different non-overlapping channels. If you do that, then when you switch from AP-A to AP-B, all the clients associated to these two APs, they will not be contending for the airtime with each other. And the threshold of this non-contention between the same channels is around neg 85 dBm. You can see that on the screen, the access point on the top on channel 1, there is like 8 neg 85 dBm shown. It's actually partially true. This is typically the case because the real threshold, it depends on the generation of Wi-Fi, but neg 85 is a good bet. It depends on the noise floor. So before you reuse channel 1, again, you want to have a gap in between these channels of at least 19 dBs. So that's what books tell us. That's where the cells from both APs will be considered non-overlapping. In the real world, different clients, they will have different hearing sensitivity. One client will hear an AP, adjacent AP on the same channel with neg 85, while more sensitive clients will hear the same AP with maybe neg 80. So for one client, there won't be any CCI. For another client, you will have channel overlapping. And the other more sensitive clients will be playing the game more nicely, where it will wait until the client associated to the adjacent AP on the same channel stop talking.
So Matt, we have a question that I want to interject with real quick. It seems to be of interest of a few of our attendees. Question is from Nick. Even if we follow best practices and deploy APs using channels 1, 6, and 11, how should we handle those situations where some of our neighboring wireless networks don't follow those recommendations and use other channels such as 2, 3, 4, 5, etc.?
That's a great question.
That is a really great question. Thank you, Dale, for asking that, and Nick for asking that as well. So what we'd recommend that you do here is that you go and do a survey using your trusty Ekahau Sidekick and your mobile device, and you do a survey of your environment, and you find your neighbors that are using these channels 2, 3, 4, 5, 7, 8, 9, 10, for example. And then once you've captured that data, you can visualize the impact that's having on your wireless network by looking at the heat maps inside of Ekahau, which we're going to be showing you later on today. So the best thing that you can do here is when you've got neighbors that are using these channels is actually try and ask them to reconfigure their wireless devices to not use those channels, and then you can show them the impact it's having on not only your wireless network but their wireless networks. And then you can explain to them that when you're using these channels, it actually makes Wi-Fi worse for both of us, whereas if we work on the same channels, we're going to have a better experience. So if they stick to channels 1, 6, 11 and you stick to channels 1, 6, and 11, then you're going to both have better experiences on Wi-Fi. Now, I know it's not always possible to go and reconfigure all of your neighboring wireless access points and ask them to use the same channels. So if that is the case, what I would probably recommend that you do there is that you move all of your business critical corporate wireless traffic from 2.4 gigahertz to 5 gigahertz and make your SSIDs that are business critical 5 gigahertz only. So you can then avoid your neighbors that are using the channels that cause adjacent channel interference in 2.4 gigahertz.
Yeah, so in short, buy your neighbors a coffee and talk them through that.
Yeah,
and
so
great question from Steve.
Coffee or pizza, and then show them on your Ekahau surveys the impact that it's having to their wireless network.
Yeah, I like what Steve said. If they refuse to make changes on their network, remove them from your Christmas list. Yeah, exactly. That's what I would do.
So recommendation, guys, and the same applies. Some of these answers that you got for whenever as we address ACI on 2.4 gigahertz, even channel bonding. If some of your neighbors are doing channel bonding on 2.4 gigahertz, you want to follow some of those recommendations so that you have a great Wi-Fi experience for not just you but them as well.
Yeah, that's a really great point that you bring up there, Dale. Like in Wi-Fi, since 802.11n came along and Wi-Fi 4, that enabled us to be able to bond two adjacent 20 megahertz wide channels together, and you can do this in the 2.4 gigahertz frequency band. So my question really is that when should you bond your Wi-Fi channels together in 2.4 gigahertz?
I know.
You know? Okay, you tell us then, Matt.
Never do that on 2.4 gigahertz. Never, ever, under any circumstance. If you do it, then you have one non-overlapping channel, assuming everyone is using the same wide 40 megahertz channel on 2.4. So never do it under any circumstance. And we have a good question in regards to what do you do when you have other things operating on the same channel as your adjacent channel. Like Jeffrey has asked, what about IoT devices? In example, I recently ran across a warehouse fan broadcasting on channel 3. And if that's a Wi-Fi device, like 802.11 device operating on channel 3, and when it's actively broadcasting something, actively transmitting traffic, it will cause the collision or collisions and retransmissions for both itself and clients on channels 1, 2, 3, 4, 5, 6, and 7. So quite a lot of overlapping there. If it's a non-Wi-Fi device, just a wireless device that happens to operate on the frequency that represents channel 3 in 2.4, then it will be seen as an interference, as noise on 2.4 gigahertz band. Actually, the next slide is a great segue to talk about certain thresholds. So there are 3 things that Wi-Fi devices, doesn't matter on what band, are going to do to respect before they even start thinking about transmitting. So as part of the listen before you talk, you have 3 different things you check. One of the things is signal detect, SD, called also a preamble detect, PD. It means that if there is another Wi-Fi device transmitting on the same channel with neg 85 around typically or higher, then the device that wants to talk, even if it's its turn, it will defer, it will wait for its turn. So that's Wi-Fi. Now, in regards to the IoT device that operates on the same channel as Wi-Fi device, but is not Wi-Fi, we have energy detect, ED threshold, and ED threshold is higher, is way higher than preamble detect, signal detect threshold. It's around neg 62 dBm. So if the IoT device transmits with neg 62 dBm or stronger from the device's perspective, from the Wi-Fi device's perspective, the Wi-Fi device will wait, it will defer, it will wait for the interference to be gone. So depending on the activity levels of that channel 3 warehouse fan, it might affect Wi-Fi clients slightly or a lot. And the third thing that devices, Wi-Fi devices, all of them, they have to respect before they talk, they have to check if other devices have finished transmitting their frames, their data, how it's being done without getting too deep.
Mac, are you finished now? Are you not finished?
Almost there.
Are you not finished? Oh, okay. Sorry, I was just trying to really badly show what happens when 2 devices transmit at the same time. And what happens is what I just did then is
I'm not sure what you're talking about.
So just like how we're having a conversation over Zoom when Mac is talking, if I try and talk when he's talking as well, then you probably didn't understand what both of us was trying to say. And that's just how Wi-Fi works as well. When 2 devices try transmitting at the same time, the receiver doesn't understand what was trying to be sent. It causes collisions, corruptions, and retransmissions. What I should have done, I should have followed the polite protocol, is that I should have waited for Mac to finish talking because I know how much longer he was going to be talking on this slide, and then I should have used my opportunity to talk. So I kind of broke the rules there, but I thought it'd be a fun little way to talk about the clear channel assessment part of step 2. Sorry, Mac, you carry on now.
No, that's fine. That's fine. I really like when you interrupt me so rudely. So the third thing is NAV, network allocation vector, and NAV is just a timer that all of the devices they set while they listen to preambles of any active Wi-Fi device, which means if an active device starts transmitting data or a frame, Wi-Fi frame, it has a duration AD in microseconds. And that duration AD sets the NAV timer, and all of the devices, they will stop playing the game. They will stop counting down, waiting for their turn for the duration of the duration ID of the NAV vector. When it hits 0, they will continue playing the game where they will still listen before they talk. Now I'm done, Matt.
Thank you very much, Mac.
You're very welcome.
So that was 2.4 gigahertz in a quick nutshell. Let's try and crack 5 gigahertz now as well. So taking a look at this chart, what we see here, I want to first break it down by the rows, and then we can talk about the bands and then the different colors. So first of all, if we go down like row by row, in the 5 gigahertz frequency band, like we could in the 2.4 gigahertz when 11N was introduced, we can bond 2 adjacent Wi-Fi channels together to create a wider channel. But actually, instead of just going to a 40 megahertz wide channel, we can actually go up to 80 megahertz wide and even 160 megahertz wide with the introduction of 11AC and 11AX. But if we just take a look at the practicality of this, because we go from having 25, 20 megahertz non-overlapping channels in 5 gigahertz If we bond the channels together, we go from 25 down to 12 40 megahertz wide channels, and then we go from 12 down to 6 if you want to use 80 megahertz wide channels, and then just 2 non-overlapping channels if you want to use 160 megahertz wide. So why would you bond channels together? This is so that you can get faster data rates, and it's not necessarily a bad thing to bond Wi-Fi channels together, so you can get the faster data rates and throughput for your Wi-Fi client devices, but not if it's at the expense of the performance of the Wi-Fi. So what I mean by that is if you decide you want to bond the channels together, but you then introduce lots of co-channel interference or channel overlap, or a bit like the same rules apply in 2.4 gigahertz, where we want to limit the amount of other Wi-Fi radios sharing the same channel as us. We don't quite have the same issue as adjacent channel interference in 5 gigahertz. We do have another problem when we start to use wide channels, and if we've got a mixture of wide channels and non-wide channels in 5 gigahertz, where we've got different primary channels on a wide channel hitting on the secondary of other channels, that is going to be causing us some issues in our Wi-Fi as well. So we need to watch out for that. So the kind of like rule of thumb here when it comes to bonding channels together in 5 gigahertz is that use the widest channel you can until you can't. And what we mean by that, if you can use 80 megahertz wide channels in your environment or 40 megahertz wide channels in your environment, and you have no channel contention, you've got really good MCS rates and good data rates and speed, and everything's working fine, then great, then you can do that. But if you do that and all of a sudden you've now got lots of channel interference by introducing these wider channels, then the chances are that the way that we've just kind of already discovered in the webinar today so far is that when you have more than one device sharing the same channel, they have to check to make sure no one else is using it. So when you introduce more and more radios sharing the same channel, it means less and less opportunity for your client devices to access that channel. So that was kind of tackling it row by row. If we now go across, and we can see that the 5 gigahertz is broken up into like 4 little mini bands. So if we take a look at the first one, which is in green, which is the Uni 1 band, then we've got another one that's in blue, which is the Uni 2A, and then another one, which is the Uni 2C, and then another one that's the Uni 3 band, and this is in green. So what are the differences between the channels that are highlighted in green compared to the channels that are highlighted in blue? And again, just really want to emphasize that depending on where you are in the world, you're going to have access to different amounts of channels, different rules, different regulations for your transmit power levels, for your regulations for indoors and outdoors. So always please check your rules and regulations. But the difference between the green channels and the blue and the yellow channels is that the blue and the yellow channels, you can see there's another bar there called DFS channels. And what does DFS stand for? And DFS stands for dynamic frequency selection. And in the 5 gigahertz frequency band, believe it or not, Wi-Fi isn't the only technology that operates here, and it's actually not the priority. DFS is basically for other technology that's using radar technology, and radar technology has the priority when it comes to working in Wi-Fi. So if we take an example of, let's say, one of our access points, when we first switch it on and we want to use one of the Uni 1 channels, let's say just channel 36, the access point can be switched on straight away and it can start broadcasting our SSIDs. And it can, and our client devices, they can connect and no problem at all. But if we, let's say, picked a channel that was inside where the DFS channels are, say channel 60 or 64, if our access point was configured to use one of these channels, it has to wait a period of time before it can start advertising the SSIDs. It has to check to make sure that there's no radar activity happening before it can start broadcasting the SSIDs. And something else to think about here as well is that if the access point working on, say, channel 60, after it's been up for a little bit of period of time, and there is then radar activity, it detects like a DFS event on that channel, the access point has to move from that channel. It has to basically put that channel into what's called non-occupancy. It has to switch to another channel. It can be another DFS channel, or it can go to a non-DFS channel, but it then has to then mark that channel as non-occupancy for a period of time, and it cannot go back and use that channel. The other thing to think about as well is that our client devices, they have 2 ways of discovering wireless networks. They have something that's called passive scanning and active scanning. And a passive scanning is when the client devices, they are just listening for the beacons that contains the SSIDs from our access points from the Wi-Fi radios. So what will happen is that your client device will go on to, let's say, channel 36. It will wait for a period of time to listen for a beacon. Beacons are sent out every 102.4 milliseconds. So typically our devices will wait on a channel for around 105 milliseconds. So it has the opportunity to capture that beacon frame, and then it will move on to the next channel, wait that period of time, and then move on to the next channel until it hears an SSID inside of the beacon that it's looking for to go and connect to. And I know 105 milliseconds, it doesn't sound like too much of a long time, but in Wi-Fi, that is actually quite a long time. And especially if you think that we've got 25 channels that we have to go and scan through. So what's the difference between passive scanning and active scanning? Or active scanning is when the client device can go onto a channel and it can send what's called a probe request. It's basically the client device going, hey, what's all the access points around me? What have you got out here? Come and tell me what you've got. And when the access points, they hear a probe request, they respond with a probe response. And now active scanning is up to roughly around 5 times faster than passive scanning, which sounds great. So why do our client devices not just do that for all of the channels? And that's because they can't. Our Wi-Fi client devices, they can only do active scanning on non-DFS channels. So what that means is that they could do active scanning on Uni 1 and Uni 3 channels in 5 gigahertz. But when it comes to the Uni 2 channels, they can only do passive scanning. So this means that to discover your access points using the DFS channels, it could take a longer period of time, which can affect things like client roaming. If you're using a time-sensitive application such as a voice or a video call over Wi-Fi, and you're using the DFS channels, and your access point goes to transition from your client device goes to transition from one access point to another access point. If that access point is using a DFS channel, your voice call could be disconnected, the quality could drop, you could miss a few packets, and yeah, you could have some issues with your voice call if you're using the DFS channel. So it's something to think about. We have actually got a checklist that I'll let Mac talk about for a couple of minutes when it comes to the DFS channels.
Okie doke. So the DFS checklist is to use DFS channels if you need more capacity, and that's totally the case. I've heard stories like, oh, just use, just use 9 channels, Uni 1 and Uni 3. Don't use DFS channels at all in like dense enterprise carpeted offices environment. Don't do that. Just use all the channels available, assuming that you can. So you not only need to do a research of what channels your clients that you are designing your network for support, because it is possible that some of the clients used in your corporate environment, they won't support some of the DFS channels. If that's the case and you need them to work on Wi-Fi, then you have to exclude those channels from your channel plan. But if they support everything, then enable everything. If you have DFS events that they affect some channels with very low frequency, let's say that you have channel 100 affected by DFS once a week, it's probably still better to include that channel in your channel plan for added capacity benefits, to give your clients more airtime, to make sure that they will be able to use those channels for the other 6.99 days until they hit this one DFS event. And then they will have some issues. But that's probably not many clients will not even notice it, but the impact is way lower than the benefits of using that channel to begin with. Remember what Matt had said about the potential impact of DFS channels, where you cannot probe on that channels, on your roaming performance. And also remember that you have roaming enhancements. You can use something like 802.11k neighbor list, where your client, before it roams, it can ask its current access point, Mr. Current AP, my threshold, my RSSI is getting lower. I want to roam to the next best access point for me. What channels should I scan? And then the current associated AP will come back to the client saying, oh, my neighboring APs are just APs on channel 100, 108, and 116. So I don't see anything else, which means that probably you won't see anything else as well. So instead of scanning all 25 channels, scan these free channels instead. So then the client says, oh, thank you. It will go and dwell for 105 milliseconds on each of these free channels, and it will find the best option to roam to fairly quickly. So that's 802.11k. Use it to your advantage with DFS channels.
We've had
That's
a
pretty much it.
yeah, I was gonna say we've had a really good question come in here that kind of relates to the 5 GHz channels, and the question is coming from Jeremy and asking that, you know, should channel 144 be used? And if we take a look at here, we can see that channel 144 is inside of the DFS channels, and the answer here is that, you know, you need to check that your client devices support channel 144, because if you have some older devices, there are some older devices out there that don't support channel 144. So let's say, for example, that you decide to use channel 144 in your design and your deployment, and you put a couple of access points on channel 144, but then you've got a client device that comes along that doesn't support channel 144. What that would look like from the client device's perspective, when it goes and even stands directly underneath the access point, it will not even hear the Wi-Fi. It won't hear the Wi-Fi. It won't even know that there's an SSID being broadcasted from your access point, even though it's physically stood underneath it, because it doesn't support channel 144. So it's really, really, really important that we check what our client devices are capable of doing for when we're doing the design. And our 3 steps to great Wi-Fi every day, step 1 is extremely crucial when you're having that conversation with the stakeholders who you're designing the Wi-Fi for, is you need to understand what are the client devices that are going to be using the wireless network. Because in this example, if we had just turned on channel 144 on our controllers, included it in our Wi-Fi designs, but then the stakeholder that you're doing a design for, their client devices, they don't support channel 144, as they move around the environment, they're going to potentially have some coverage holes, some coverage gaps, because they don't see the SSID being broadcasted from one of the access points that's using channel 144. So it's really, really crucial that we understand what our client devices support for what we're designing the wireless network for. So that's why it's really important. You have this conversation, you check the manufacturers' data sheets about what channels they support. Unfortunately, not all of the manufacturers put on a data sheet what channels that they support. So sometimes you might need to do a wireless packet capture. You can use the Ekahau Sidekick and the Capture app. And what you want to do is capture the association frame from that client device and have a look through that packet capture. And inside of that association frame, it's going to tell you what the client device is capable of. And you can see the channels that it supports. And if you see, for example, maybe it doesn't support 4 of the Uni 2 DFS channels, then you could just exclude that from your design, exclude that from your wireless controllers for your implementation as well. So a few tips there. Oh, Matt, can we have a poll question?
We do have a poll question. So let me quickly launch a poll and let your favorite poll read the poll question. So what is your biggest challenge when it comes to channel planning? A, meeting my channel interference requirements. B, AP using white channels by default. C, concerns around using the DFS channels in 5 GHz. Or D, stakeholders want to be able to have fast speed test results.
I'm looking forward to seeing what everyone answers on this one.
I like those answers so far.
Oh, funny. There's a reason why I put one of the answers here. So I'll let Mac stop the poll and share the results before I talk through, because I don't want to influence any of the answers here.
Okay, I'm ending the poll now. And sharing results with everyone. There we go.
So yeah, amazing. I mean, it seems like pretty much half the people that voted say that, you know, the meeting your channel interference requirements is their biggest challenge, which yes, it can be a big challenge. And we're going to show you in a demonstration very soon how hard it can be to meet your channel interference requirements, especially if you're designing for multiple floors, which we're going to be showing you inside of Ekahau very soon. But the reason why we put that question in the D is that stakeholders want to be able to have some fast speed test results, is because this actually happened to us, didn't it, Mac, where we did a design for a customer, and they had a perfectly working wireless network. We'd done the design, we'd done the implementation, we configured it, and it was all working perfectly, like no channel interference, but we were using 20 megahertz wide channels on 2.4 and 5 gigahertz. And then after we had done the deployment, we got a phone call from the customer, said, "Hey, Mac, just want to call about the problems that we're having with the Wi-Fi." And I said, "Oh, really? What's the issues that you're having?" And they're like, "Yeah, when I do like a speed test now, I get really slow speeds compared to what was in the office before that we had." And I was like, "What do you mean you get slow speeds?" Like, "Yeah, when I do a speed test, I get like 100 meg download, whereas before when I was doing a speed test, I could get like a few hundred meg." And I was like, "You know, you called us to complain because the Wi-Fi sucked at the where you was before, because they were using really wide channels, which meant when they did a speed test, they could get really fast speed test results. But the actual quality of the Wi-Fi was very bad because they had lots of contention, they had lots of overlapping primary and secondary channels, and it was just a bit of a mess." And when we did a design, perfect implementation, no channel interference, it was all working perfectly. But the stakeholders, they wanted to have fast speed test results. So they really wanted us to use wider channels so they could get the faster data rate. So yeah,
But also
not
at
sure
the
if
same
that's...
time, the requirement for that network was voice and video. So what we've had to test the new network with Matt was to get on a conference call, like a Zoom or whatever they were using, and we were literally running around the office to check if the roaming is fast enough for the conference to be maintained, and it was spotless every time, even during the normal operation hours with the office full of people pre-COVID times. So yeah, we
Yeah,
have it.
I almost couldn't believe it, but I'm not sure if that's happened to anyone else that's on the webinar today. If you've had that same issue, let us know in the chat if you have. And yes, our favorite part of the show, we're going to do
Shall we answer some questions before we move there? Very quickly, once you're opening up your beautiful EcoHub application, we have a question from Chris. Does EcoHub recognize that some APs do not support all channels and therefore exclude them from channel planning algorithms for that AP? So the answer to that is that for the AP, EcoHub will not exclude the channels, but it will exclude channels for different regulatory domains. So if you go to your preferences of the EcoHub Pro application, you can select different reg domain. And now Matt has it set to United Kingdom, but if he switches it to, let's say, India, he will have just 4 5 gigahertz channels available to him for his designs. If he switches to Japan, he will have 14 2.4 gigahertz channels available to him. So yeah, I think that answers that question. And very quickly, another question, Peter asks, besides the effects of interference in dense environments, would the applications being used by clients also be consideration for channel widths above 20 megahertz? How is this determined? So the quick answer is that for most applications, throughput that 20 megahertz channels give you is more than enough. Clients, they need less throughput than you would imagine they do. So your client might tell you that they need to have, 300 megs per client, but it's not the case. Typically, if anything in enterprise environments, all you need to do is to have a Zoom call like this one, maybe with some screen sharing, with few cameras. You have to support web browsing, office applications, emails, and with a typical usage, you don't exceed like 2 megs. For example, now I'm using close to 1.5 meg on a Zoom call. 1.5 meg. So 20 megahertz is plenty. But if you can use wider channels without introducing excessive CCI, cross-channel interference, do it. It's better to have a network with CCI of, let's say, 2 for most clients than having 20 megahertz channels with no CCI in most cases. But when the CCI starts to grow to 3, 4 or more, then it will, the benefit of bonding channels and having more than twice the throughput as a result of bonded channel will start to fade because of increased contention. When clients, when they want to speak, when they want to transmit, they won't be able to because there is someone else transmitting on the same channel. So it's just like a fine game of balance. Okay?
Okay.
Back to you, Matt.
Thanks, Mac. Okay, so if you've not seen Ekahau before, this is our, like Mac said, beautiful, amazing Ekahau Pro. And what we're going to do together on the webinar today is we're going to do a design for a multi-floor building. So creating a 3D building inside of Ekahau. So I have, for the purpose of time, I have already done that. And what we've got here is we've got a building called the Ekahau HQ that has 3 floors, floor 2, floor 1, and floor 0. And what I've done is I've vertically aligned my floors, I've scaled my floors, I've already drawn all of the attenuation materials for the windows, for the concrete walls, for the dry walls, for the doors. We have done all of that already so far. So we are now ready to start to do a design. So I want to show you how we can do a design for across multiple floors, and then take a look at how we do channel planning across multiple floors as well. And I will show you a few of the ways that we can change and fix channel interference issues inside of Ekahau. So first of all, just wanted to show you that we've got our building configured and it's all green. Okay. So what I'm going to do now is what I want to do first of all is I just want to place an access point, and I've got an AP here. I'm just going to use this Aruba access point. And what I'm going to do is I'm actually going to place it on the top floor, so floor 2, and I'm going to place it directly above this point here, which is called the atrium. So what we can see here now is the predictive coverage from this access point that is above this atrium. And if I go down from floor 2 now to, let's say, floor 1, what we can see here now is that there's bleed through from the floor. So from floor 2 down to floor 1, and also if I go down to the ground floor of floor 0, we can see that it bleeds through the floor to all the way from the top floor to the first floor, and we can hear it down on the floor 0 as well. But what you might have noticed here that we've got is something that's called an atrium. So we've got an atrium that is right here. So what I need to do is I need to tell Ekahau, actually, there's a big hole in the floor here, and there is nothing to attenuate the Wi-Fi from the floor. So what I'm going to do now is I'm going to come underneath the planning tab, and I'm going to switch to this option that is called the hole in the floor tool. And whatever I do, if I draw this now, where the atrium is here, and I come over to here and I finish drawing it, we now see no coverage above the atrium here. But if I move the access point, say, back to where it was before now, and we go and look at, say, floor 1, we can see that the coverage comes through way more now onto floor 1, because we've said to, hey, Ekahau, there is nothing here to attenuate the Wi-Fi from the ceiling of floor 1. And if we go down to floor 0, we can see that the coverage is coming through way more now to floor 0. But we actually have 2 atriums. We have an atrium on floor 1 and floor 2. So what I'm going to do is I'm going to create another hole in the floor right here. And once I've finished, and if I go back to floor 0 now, what I can see is that the coverage comes through way, way, way more now, going through from floor 2 all the way down to floor 0. Okay, so what I'm going to do now, go back up to floor 2, and let's get rid of this access point, and let's pick another access point. Mac, what's your favorite access point?
My favorite access point, missed AP43, please.
Sure. So I'm going to type in missed AP43. I select my missed AP43, and what I'm going to do now is just simply place a few access points, making sure we meet our coverage requirements. With 3 APs on the floor 2, I can see that I've got primary coverage. I've got my secondary coverage. Oh, not quite over in this corner. So maybe I need to rethink my design slightly. Pull this access point maybe over to here a little bit. And now I'm happy that I've got my, coverage requirements being met nice and easily on my top floor. So how about for the floor below? Oh, quite a lot of coverage there, but I don't necessarily want to rely on coverage from the floor above to cover my floor below. So I'm actually going to place some more access points down here as well. And I'm probably going to place them in like a similar position. So 3 APs, I'm quite happy with that. And then if I go, actually, I just want to turn off the Bluetooth radios for now, make it a bit cleaner. And then I want to place some access points down on floor 0 as well. So again, we'll go 3 more access points, one in the big conference room, 9 APs now. I'm very happy with my design. I've got my primary coverage and my secondary coverage working very nice everywhere. So if I go back up to my top floor, the next thing I want to look at though is, am I meeting my channel interference requirements? So now if I go to channel interference view, what we can see here is that it's great everywhere. And we're looking at the 5 gigahertz frequency band at the moment. And it's failing because all of our access points by default, they go into channels 1 and channel 36. So what I need to do is I need to start changing the channels of these access points. And I'm going to start with the 5 gigahertz access points. So what I can actually do, if I go over AP1, what I can do is I can right click on the access point and go to edit access point. And the option I can do now for the 5 gigahertz radio is radio 2. So what I can do here is I can come here and I change it from channel 36 to, let's say, channel 40. If I close it, it has now changed the 5 gigahertz radio for channel AP1 on to channel 40. I can do the same for AP2, go edit access point. I can move it on to, say, channel 44, close. And then we saw a little bit of change happen here. So if I hover my mouse over here, we've got 6 other interfering radios on the same channel. But if I go over here, how many have we got? 5. Okay, so we're starting to fix the interference slightly. Let's do one more for AP3. Let's change it to be on channel 48 on 5 gigahertz. If I hit close, but we've still got problems because we can hear the other access points on the adjacent floors. So what I need to do is I need to come down to, let's say, floor 1, and I need to change the channels on these access points as well. There's another way that we can do this. If I come over to, let's say, this view on the left-hand side where the access point is, if I highlight simulated AP4, if I just click on this radio here, it gives me the option to change the channel. So I can change the channel directly from here to, say, channel 52. If I move on to the next AP, which is AP5, I can move this one on to, say, let's say channel 56, and then channel AP6, I can move that on to, say, channel 60. But we've still got channel interference, and that's because if I go down to floor 0, all of these access points, they're still on channel 36. So what happens if I change these APs to be on a different channel? I'm going to go channel 100, and we've got some green that starts to creep in. Okay, how about for AP8? If I change this one to, let's say, channel 104, everything is now gone green. If I hover my mouse over the map, what's happened now is that we've got no channel interference. So we are very happy now on 5 gigahertz that we've got no channel interference. But how about on 2.4 gigahertz? Well, yes, we're going to have some channel interference on 2.4 gigahertz because we haven't changed the channels yet. So we could take a similar approach where we just go around and just switch off or change the channels manually one by one. But that is only 9 access points. It took a little bit of time. If you're doing a design where you've got 100 access points, 1,000 access points, you don't really want to go around and just change every single one manually. So we have actually got a way faster, way cooler way that we can do channel planning inside of Ekahau. And if I hover my mouse over this icon here, it's called the channel planner tool. And what I do, if I click on it, it pops up this automatic channel planning wizard. And what we can do here is we can do a design for both frequency bands, or if I just wanted to focus on the 5 gigahertz, I could select just 5 gigahertz. We have another option here that says disable any unnecessary 2.4 gig radios. We can then pick what channel plan we want to do, like a 1.6.11, a 1.5.9.13. Remember, we always typically want to stick to a 1.6.11, so I'm just going to leave it as that. And then we have the option for 5 gigahertz. So we did a design using 20 megahertz wide channels. But what we can do is we can change it from being 20 megahertz wide to 40 megahertz wide, 80 megahertz wide, or 160 megahertz wide. I'm not going to change that just yet because now we've got the option for selecting the 5 gigahertz channels. And the question that we had earlier is that, should we include channel 144? And again, it depends on if your client devices support it or not. But if you did your check and you found that your client device didn't support channel 144, we can simply not include channel 144 in our design by unselecting it from this here. Maybe your client devices don't support channels 140 as well. You can unselect that too. And then now if we change from a 20 megahertz wide to a 40 megahertz wide, what it does, it groups the channels together. You will see it reduces the amount of channels that we can use on 5 gigahertz. If you go to 40 megahertz wide to 80 megahertz wide, again, it reduces the amount of channels that we can use. And if we want to do a 160 megahertz wide plan, we absolutely can, but I'm not sure I would recommend that for any environments, maybe other than your home environment if you live miles away from everyone else. But let's see if we can get...
Even if you do live miles away, like in the middle of nowhere, it will increase the noise floor to the point where your usable SNR might drop and your MCS rate might drop. So every time you bond channel, you lose SNR, your SNR will be lower. And your retransmissions might take all the benefit of bonding channels all together. Even for me, when I'm sitting at like around next 60 dBm, slightly away from my AP, it's better for me to use 40 megahertz than it is to use 80, even though I have no neighbors using 5 gigs.
Yeah, so what I want to do now is I want to see, we've got a 20 megahertz wide channel plan that works in this environment, no problem at all. But I wonder if a 40 megahertz wide plan would work. So what I can do is I can select 40 megahertz wide. And when I hit create a plan now, and what you'll see is that all of the access points, they changed their channels. And what's happened now is that Ekahau has disabled some of the 2.4 radios, and it has also put the 5 gigahertz radios onto onto 40 megahertz wide channels. And the reason why I know these are 40 megahertz wide channels is because it's gone from this at symbol shows me this using now channel 108 at 40 megahertz wide. So with a simple click of a button, Ekahau has now come up with a design that meets the requirements for our channel interference. So on 2.4 gigahertz and 5 gigahertz, we've got a 40 megahertz wide channel plan that meets the requirements just as simply as just running the channel plan. Should we see if an 80 megahertz wide plan works? So since it's so quick, why not? I'm going to click on the channel planner tool. I'm going to go from 40 megahertz wide to 80 megahertz wide and create another plan. And oh no, we've now got channel interference. So if I hover my mouse over here, we have now got channel interference. We've got 3 of our own wireless access, our wireless APs all on the same channel. So remember earlier before when we said use the widest channel you can until you can't. This is exactly what we meant. I've now gone to an 80 megahertz wide channels and it's now caused channel interference. So what I should do in my design, go back to 40 megahertz wide channel plan. That worked, no issues. That's what we should use. So that was all the demo that I wanted to do today around channel planning inside of Ekahau. Mac's going to show you some awesome product updates that we've got with Ekahau Insights that's only launched this week.
You mean yesterday? So guys, before I share, actually let me share and then answer one more question. So I am sharing my Chrome. It's disappeared on me now. But before I go there, there is one interesting question from Peter. I think it's another question from Peter actually. Some manufacturers ship their APs with 80 megahertz channel width as default and claim that once interference is encountered, the width will automatically be reduced to 40 or 20 megahertz by the wireless LAN controller. So why go with a fixed value? Is that the controllers are not aggressive enough? So that's a very good question. And the answer might be as long as the entire webinar. So I'll try to keep it super short this time. There are vendors that are doing it better than the others. Some are better than the others, but it's not unusual to see an out-of-the-box Wi-Fi wireless LAN that has a mixture of 20, 40, and 80 megahertz channels. And while it might seem like a good idea to have wider channel in more heavy used area, actually having mixed widths of your channels, it can introduce 2 issues. First issue, it enables protection mechanisms. Every single frame will be using request to send, clear to send frames that are preceding any data transmissions, and that adds to the overhead. So we have less time for data and we are using more airtime for control and management frames, which is not a good thing. And another thing is we can, without diving too deep, again, I'm trying my best, is we can introduce primary, secondary channel overlapping, where some channels, let's say when you have channel 36, 40, 44, and 48 bonded into 80 megahertz channel, and then you have some 20 megahertz channels, one of them overlapping with that 80 megahertz on channel, let's say 44, when the 80 megahertz at 36 and 20 megahertz at 44, they overlap and they have something to transmit. They will both be transmitting on top of each other, creating retransmissions, collisions, and slow Wi-Fi for everyone. It's called the primary, secondary, or BSS. So that's another important thing to have on mind. It is a best practice not to mix different channel widths in your wireless LAN environments. So having said that, you probably had some time to peek at my screen, and guys, we have a huge news for you. This is Ekahau Insights, and what you are looking at now is a design project opened in Ekahau Insights. It's a big thing because up until yesterday, you can only view the survey files and not the design files. Now you can share both design and surveys, which is a massive thing. So try to imagine sharing your projects, even designs, with your customers. They might not have Ekahau licenses. You can still share it with them. You can send them an email with exec summary and follow it up with a link to a project. You can share it with them through Insights. So they're being sent an email with a link that they can access it. And they can just take a look at your design. They can take a look at the placement of the APs, models of the APs, models of the antennas used. And that's a massive, massive thing. Even if you're not interested in reporting for Insights, this is a very sleek view. You can click on the area, you can see the requirements specified. You can highlight each and every access point and see signal strength from one or more APs. If I deselect the AP, that it shows for all my APs there. You have different visualizations. So for example, I can see that the coverage here is amazing, but how about channel interference? And it's all gray. It's quite massive. It looks like it's like 3 or 4 or even more. You can see network health all red because of network issues, channel interference. We didn't have that for design files before. So now, if I wanted to share this particular file or a survey file with a team of people that you might be sharing files with on quite frequently, maybe with more than just one person, you can create a group of people now. So when I go to profile and license, I have my sharing group. I've just added Matt there because I have no other friends in life. But if I had a massive team of Wi-Fi engineers and I wanted to keep on sharing files with them, I could add them all here to the group. And then when I go back to my project and I hit sharing, where is it? Where is my sharing?
Click on sharing.
Yes.
I think it might be because I'm the owner of the project. So
that's the case. Yes.
Yeah. So yeah, when I've shared it now, I can share it to the group. If you pick another one.
Okay, there we go. That's a good shout. So that's a project that I'm an owner of, and I can share my file with my group, all of the people on the group. So if it's your employees, for example, and one person leaves the employment, you can just remove that one person from the group, and the access to all the projects that you've shared it with the group sharing functionality will be revoked, which is a great thing. So guys, look around Insights. It's changed quite considerably. You can view different bands like 2.4 and 5 now. You have new notifications button, so I can see what's changed by who and when. You can even set notifications to send you a daily email. So these are quite big improvements when it comes to your workflows using Insights.
And
yeah,
Matt,
and the other thing actually, oh, sorry,
no,
go ahead, Dale.
sorry. I was just going to say we got an interesting question while you are presenting Insights. The views there, Chris asked, are they mobile device or as measured views within Insights?
So that's a good question.
Yeah, this will be measured what you've got inside of your. This will be the what you've got inside of your design file set. So typically, it's going to be not using the mobile view in this option right here. But the one thing I just wanted to call out as well is that you can share your design project files now with people that don't have an Ekahau license. So if you need to share this with people that may be doing the installation for your design, you can share this file with them and they can access everything that they can see here. They can see the bill of materials, the height of how the access points are supposed to be installed, the ceiling. And Mac, if you just press on that one of those blue little icons next to it, you can locate particular access points on the floor plan, which is a really nice way to be able to find out, where is this specific AP that I need to install with an external antenna. Improvement. So go check it out. Before we wrap up the webinar, we actually wanted to do a little giveaway. So if you want to enter to have a little giveaway for a chance of winning one of these amazing Ekahau wireless design notepads that I use on a daily basis, all you need to do is scan that QR code and post onto your Twitter the post that's in there from Anita Ruta. If you don't have Twitter, use LinkedIn. Just you can just copy the the post that we've got there and post it on LinkedIn as well, and just make sure you at Ekahau or use the hashtag Ekahau. Yeah, there's a question. Is that with real paper? Oh yeah, there's real paper in here. Lots of real paper.
Quite shocked, Matt. Like, you are quite young and you are using pen and paper. I'm quite old compared to you, and I don't.
Yeah, I like to mix it up sometimes. So yes, if you'd like to enter, please go onto Twitter, go onto LinkedIn, just post about what you see there, and we're going to pick away 15 winners to get a free notepad. So we are at the top of the hour now. So what we can do is we can take we can answer a few more of the questions that came into the Q&A. So if you'd like to stay on for a few more minutes, we'll try and get through some of those extra questions. But if you're dropping off and leaving us now, we really hope that you enjoyed the webinar today. Stay tuned for our next webinar. We're going to be demystifying Wi-Fi even more, but this time around how you do Wi-Fi surveys. So make sure you tune in for that. And then, yeah, Dale, any particular questions in the Q&A you would like to... Max, stop sharing now, so everyone can see Dale's lovely face.
So yeah, one of the ones that I'm reading right now is, can we check the scaling for a floor plan via Insights? So that's a very good question, and also a good call out. We aren't able to view the scaling in it, but it is in the cloud, so you can pull and retrieve that into Pro to view such detail. So that's my answer for that question. Yeah, also on your mobile device as well. So if you're using the survey app on your iOS device, you can check the scale, you can edit the scale of all of your projects, even from your mobile device. So you can change the scale, view the scale if you need to on your mobile device and in the Ekahau Pro application.
Totally. Let's smash one more question, guys. A question from Mike upvoted: how much should you trust the Auto RF planner and power software built into most enterprise WLAN controllers or APs? Or is it best practice to static assign? The question is, as always, St. Clement's style, it depends. But if you use wireless LAN controllers or cloud controllers to control your transmitting power levels and channels allocation, some vendors, they do it so perfectly that you don't need to touch it. Some vendors, they require some love. But if you specify, let's say, use only 20 megahertz channels, do not exceed 14 dBm on 5 gigahertz, for example, then your RRM, radio resources management, or whatever the vendor calls the protocol that does transmitting power levels and channels allocation is, it will work very decently. However, in some environments, like we've done few massive warehouses where the environment won't be changing. We know exactly what they have there. They don't have any neighbors. We know what devices and interference they have there. It might be better to do a static channel plan so you don't change channels in the middle of the operation. And some warehouses, they are operating on 24 hours basis and have very critical Wi-Fi. They have autonomous robots doing stuff in the warehouses. And when you have unplanned channel change, it can affect your production, for example. And also, like some vendors, they allow you to anchor your time of the RRM change to a specific hour. So let's say you can say only allow your controllers to change the channel that it was itching to change throughout the day at 6 o'clock p.m. once a day. And that's outside of your working hours, and it's absolutely fine. Also, since we are discussing it here, when you do a validation survey, always freeze your RRM so you don't have channels changing on you whilst you walk around.
A question that we got in there is, where can we get one of these awesome, cool 802.11 t-shirts? And if you head over to the Ekahau website, our swag store, you can go and get one of these 802.11 t-shirts from our swag store. We have our amazing Ekahau marketing team on their chat. They're putting links to it now. If people are asking, this is a brand new piece of swag if you'd like to go and get yourself a t-shirt from the swag store. Any other questions we want to take before we wrap up the webinar today? The product team have done such an amazing job making all these t-shirts, haven't they?
Yeah, I love them. Vintage style. I love it. It's good. It feels good.
Here's one question about within Insights. Can they pull design by a colleague and make edits or just view? So the owner of that project in Insights can assign permissions. It could be full rights, or it could be read only, or they can completely transfer ownership of that particular project, in which you have full rights to edit or modify that project accordingly. Good question.
Great stuff. Do we want to have one more, Mac?
Just looking at the questions upvoted. There is no upvotes, so let's just
Okay,
wrap up.
call it a day. Call it a day then for today's webinar and see everyone on the next one.
Yes, please. Okay, guys, we had a massive blast, of course, a Wi-Fi blast, having everyone on our webinar. It's a great pleasure to have so many attendees every second week. It's an honor to have everyone. Great effort, team effort from Ekahau marketing team. So thank you very much, everyone. And we will see you back in 2 weeks' time.
Yeah, and a special thanks for Dale for helping us out today. Did a great job hosting this with us. So thank you, Dale, and thank you everyone for joining us. We'll see you in 2 weeks' time on the next one. So see you all then. We're going to hang up the webinar now. Bye, everybody.
Bye.
Everybody.